Section 3.8. So far, we have done differentiation with functions that are explicitly defined. What do I mean by explicitly defined? Well, functions that look like this: y equal, for example, 3x to the 4th power minus 2x to the 3rd power plus x minus 7, let's say, right? These are the functions we are used to deal with when it comes to take derivative, right? And then if they ask you to take the derivative, this will be 12x to the 3rd minus 6x squared plus derivative of x1, derivative of 7, 0, right? Done, right? That's very easy, straightforward. Well, we have formulas for that. We have a lot of formulas to deal with this when the function is explicitly defined, meaning the function shows y isolated on the left and the rest on the right, right? Yeah, great. However, there are functions that are implicitly defined and not directly defined, but somehow indirectly defined, right? Functions like y in this equation, x squared plus y squared equal 25, right? Y is still a function of x, but it's just that we don't have it written in this form, right? These are called implicitly defined functions. In order to get a derivative of these implicitly defined functions, we must follow a method called implicit differentiation, okay? They're gonna explain now. But first, before we go into the method, I want you to have clear when a function is explicitly defined or when a function is implicitly defined. So explicit functions are the functions we've been dealing with so far, right? Y equals some function of x, y is isolated, right? Examples: y equal to x cubed minus 8x squared plus 1 is an explicit function, right? This one, y equal cosine of x minus 6x squared, explicit function. Y equals 7 tangent of x minus 4x to the 7, explicit function. We know how to take the derivative of this function. But what are implicit functions? These functions are going to be defined via an equation in which you will find terms containing x and y, right? And these expressions containing x and y may be equal to some other expression also containing x and y, right? For example, this x squared plus y equal 36 is a function, y is a function implicitly defined, right? Not explicitly defined, but implicitly. The function y appears somewhere inside the equation, right? Here another example, look, 3x squared plus times y plus tangent of x equal y squared minus 4x. Right? Y appears somewhere inside the equation. It's not like y is equal to something in terms of x, right? It's just defined via an equation. Here the same, right? Similar, 2x cubed minus 5x times y equal y to the 5th minus 1. The key is to think of this guy, y, as a function, some function of x. We don't know explicitly what it is, but it's some function of x, okay? It's what mathematicians call that dependent variable, right? Independent variable x, but dependent variable y. So we gotta be careful when you take derivatives here when we have terms containing y. I will tell you how to do it. All right, so in order to get the derivative of an implicit function, a function that appears somewhere as part of an equation, we follow this method that comes in 2 steps. It's called implicit differentiation. And the steps are, first step, take derivatives with respect to x on both sides of the equation, in both sides of the equation. It's better said, in both sides of the equation. Step 2, put together all terms containing dy dx, which you are looking for, right? The derivative of y with respect to x. And step 3, 3 steps actually, solve for dy dx, okay? 3 steps. Example here. suppose they ask you to figure out the derivative of y with respect to x, where y is an implicit function defined via this equation, x squared plus y squared equals 16. Solution. Let's follow the method, right? Let's follow the method. The method says step 1, take the derivative of the left side, take the derivative of the right side. Look, derivative with respect to x of the left side, since these two guys are equal, should be equal to the derivative with respect to x of the right side equation, right? That's the first step. So let's do that. Let's distribute our derivatives over, right? This will be derivative with respect to x of x squared plus derivative with respect to x of y squared, right? And who can tell me what is this derivative? Derivative of the constant function 16 with respect to x. Anybody?
0.
0, 0. Very good, Adriana. Very good. Yeah, 0, right? The derivative of a constant function is 0. Excellent. Now, this derivative, since my expression contains only x, is easy to take because it's the usual derivative, twice x, right? Twice x here. However, guys, here you have to be careful. Remember, y is not an independent variable. Y is some function of x, okay? So when you reach this point, when you have to take the derivative of an expression containing y, do this. Take the derivative of this y squared, thinking of this, we're gonna write this as a note here, as an outside function, the square, as the inside function, the y, right? Do this carefully, I will show you. Look, when you take the derivative here, think of taking this derivative this way. Derivative of this guy is gonna be this square, outside function the square, inside function y, inside function y. So therefore, the derivative of the outside function should be twice something raised to 1 less 1. We don't have to write it, right? Inside function here times the derivative of the inside function, right? Derivative of the inside function. This is the chain rule. So this is what you get. 2y times, let's put a 1 there so everybody can follow. So you get 2y dy dx. Now, if it's hard to understand this for you guys, that this is in reality a composite function, follow this simple rule. Look, if you are taking the derivative of an expression containing y, take the usual derivative that comes to mind, which is going to be 2y, right? 2y. But then attach this dy dx, because you are not taking the derivative with respect to x of a function depending or written in terms of x. You are taking the derivative with respect to x of y squared. This is not x, right? So because of that, you have to attach this. You take the derivative that comes to mind, 2y, but then you multiply by dy dx, right? This is like a practical rule to deal with terms containing y. Right, that equal to 0. Then the last step is just to isolate this guy, right? Isolate this guy. We have to isolate this. And this is actually the goal, right? To find the derivative of y with respect to x. So isolate now this. Yeah, so maybe we should write this a note, because a lot of times students ask me this note. When taking derivatives of functions of expressions containing y, expressions containing only y, attach dy dx. Write the derivative that comes to mind, 2y, right? But attach dy dx, right? All right, now we have to isolate dy dx, right? This guy. How do we do that? Well, subtract 2x in both sides of this equation. So we'll cancel these guys and will give us 2y dy dx equal minus 2x here, right? Minus 2x plus 0 is just this. And finally, guys, divide both sides of this equation by 2y, right? To isolate this completely. So final answer, dy dx will be equal to, simplifying 2 and 2, minus x over y, right? Final answer. I want you to catch something here. Before, when we were taking derivative of functions that were explicitly defined, the result was only in terms of x, right? But a common feature of implicit differentiation is that the result will depend not only on x, but also on y, okay? So as you can see here, minus x over y is the derivative, right? Yeah. So try to keep that in mind. So we'll be right here solving for dy dx, we get this guy, right? This is the answer. All right. Here is another one, a little bit more complicated, and then I will let you practice. What if they ask you to figure out the derivative of this y function implicitly defined via this equation, right? Find dy dx. Let's follow the steps as before, right? This is my function. Step 1 says take derivatives in both sides, right? Derivatives in both sides with respect to x, And this step kind of makes sense because if these two guys are equal, the derivative should be also equal, right? Very good. So what is the derivative of x to the 4th? 4 comes up front, 1 less stays 3, right? No problem taking derivatives of expressions written in terms of x, right? This is just this. But here, however, you have to be careful because your expression contains y's, and taking the derivative of tangent of y with respect to x. So remember the practical rule that I gave you. The derivative that comes to mind for tangent of y, knowing that the derivative of tangent is secant squared, is just this, right? Secant square of y. But since this is not x, it's y, right? You have to attach dy dx, right? It's like the derivative of the inside function. All right, now next step is just isolate this guy, right? Isolate this guy. Now isolate dy dx, right? For that, what we're gonna do is I'm gonna divide both sides of this equation by whatever this is. This here, secant square of y. This will cancel this. This will cancel this. And as a result, I will have that dy dx, the derivative of y with respect to x, will be equal to what? 4x to the 3rd power over secant square of y, right? And that's it. Now, one more time, as you can see, the final answer depends not only on x, depends also on y, right? Which is a very common feature of implicit differentiation, right? Yeah. There are more examples here, but I want you to practice now. So let me go to the worksheet, okay? Worksheet, which is here. And let's practice, right? Can you try? I did something similar to this, so probably we can try this now. I will write it for you bigger here. X to the 6 equal cotangent of y. And you are supposed to find the derivative of y with respect to x, right? Recall recall derivative of cotangent of x with respect to x is minus cosecant square of x, right? Use this if needed, right? Remember, the first step is to take derivatives in both sides with respect to x, right? So start with this. I complete this. And the second step is to isolate dy dx, right? By combining like terms. So try to do this. Number one there. Yeah, it's not that you remember the formulas. Oscar figured this out. Adriana better. Yeah, Oscar, you have to adjust. There's something there that is, you were very close, but you have to adjust. Adriana, you got it right. Yeah, now Oscar, correct. Adriana, Sarah, right? Very good, very good. Very good, guys. Yeah, just remember when you take the derivative of an expression containing x is the usual derivative, but when you take the derivative of an expression containing y's, attach the dy dx, right? The derivative of the inside function. Yeah, very good, guys. So, yeah, let's do this together so we can go over more examples. Derivative of the left side will be just equal to 6x stays with one less on the exponent. As exponent takes to the fifth, right? This is this derivative. Derivative here. Here you have to be careful, right? The derivative of cotangent is minus cosecant squared, right? But since we are dealing with the expression containing y, remember, we have to multiply this by dy dx, right? Dy dx. Next, we have to isolate this guy, right? Get this by itself. To do that, I am going to divide both sides of this equation by minus cosecant square of y, right? Minus cosecant square of y. So this cancels with this. And final answer, dy dx should be equal to 6x to the fifth power all over cosecant square of y. There's a minus there. The minus, mathematicians like to place it in the middle, right? So this should be it. And this is a perfect match with A, right? Yeah, very good. Yeah, now, sometimes they will ask you to do this using product rules. Look here, x times y. It's a product of two functions, right? X times y, again, product of two functions. So let's take a look at that, right? Yeah, but before we do that, probably we should do this. Can you try this? And then we'll deal with the products. X equal secant of 4y. Okay. Find dy dx. The function is an implicit function, right? It's inside this equation. So, and the hint is start by taking derivatives in both sides, right? Derivative here of x with respect to x, and here derivative with respect to x of this part, secant. It's a little bit tricky, guys, but I hope you can handle this for y. And I'm going to give you hint. Derivative with respect to x of secant of x is just secant of x multiplied by tangent of x, right? Tangent of x. Yeah, is this. Right? It's in our sheets. You can look at that. Yeah, try to figure this out. and then we'll deal with the products, okay? Tricky, that then in the end, I think you have to use some trigonometric identity. Mhm. Reciprocal identities you must use. Mhm. Mhm.
What question is it?
Which one do you say? Which choice?
A?
A, number 4. Let's check. Let's check.
I'm not
Good choice. Yeah, it's okay. You don't have to write. No, but it's very close. I think you missed something there. I think they have to apply the trigonometric identity, but it was very close. Yeah, let's do it together so we can take the second break. Okay. Yeah, let's do it together. Look, yes. Adriana, who is speaking? Adriana, right? Or Sarah?
No, I said
Sarah?
it's D.
Ah, yeah, now it's correct. Well, no, close again. Yeah, the answer is this, okay, for this one. Yeah, but I will explain step by step, okay? Yeah, so derivative of x, so that's the derivative of x. That's just 1, right? The identity function 1. The derivative of identity function is just 1, right? Yeah, very good. Now, this is 1. Derivative of secant. Derivative of secant is secant multiplied by tangent, right? So we do secant of 4y times tangent of 4y, right? That's the derivative that comes to mind, right? But remember, we are dealing with the expression in terms of y, not in terms of x. So we have to attach dy dx, right? This is because of the chain rule, right? Yeah, great. Now I have to isolate this guy. I have to get this guy by itself, right? So I gotta move this to the other side, dividing, I gotta eliminate this. So in order to do that, I'm going to divide both sides of this equation by this precisely. Secant of 4y tangent of 4y divisor here. And here, believe it or not, guys, the same. Secant 4y tangent 4y. Right? This will cancel this will cancel this, giving me dy dx by itself, okay? And here comes the tricky part, guys. This will be 1 over this whole thing, right? Secant of 4y multiplied by tangent of 4y, right? Agree? But now, what is this? What is this? Well, 1 over secant. What is 1 over secant in trigonometry? Remember, 1 over secant. 1 over secant. Cosine, Adriana. Thank you, Adriana. You made my day. Cosine, right? Cosine. Yeah. And don't forget also this, right? When I took the derivative, I was supposed to multiply here by the derivative of the inside function, right? But that's not a problem. But the derivative of the inside function, this 4y, is composite function, is a 4, right? So this is a 4, there is a 4. Yeah, but then that 4 then should be included here in the division, right? So 4 division by 4 here, by 4. Let's put the 4 up front, but doesn't matter, right? Yeah, 4 will appear there, right? This will cancel this 4. Again, this is because this is a composite function. The derivative of the inside function was 4. Okay. Now, therefore, go ahead.
And then you do the dy dx.
No. Remember, this guy is secant, is an outside function, right? Secant, outside function. But there is an inside function for y. So this is the derivative of the outside function. The derivative of 4y, the inside function, 4 dy dx, right? Dy dx after that. Yes. Okay. Right? Yeah, great. Okay, but then to isolate dy dx, I have to divide by this guy, but also by 4, right? By 4 here. So this is what I have done here. So I'm close to the answer. So it will be 1/4, right? 1/4. This is the first 1/4 of what? For this guy, 1/secant cosine, right? Cosine of 4y. That's that. Now, what is 1/tangent? 1/tangent now. 1/tangent. Anybody could tell us? 1/tangent in trigonometry? Cotangent. Excellent. Right, I see, guys, you remember cotangent, right? So this will justify the cotangent here. Cotangent, a very tricky problem. Yeah, I hope you remember this, guys, for your homework. Yeah, this is it, right? This is the answer, and that's why is this cosine of 4y times cotangent of 4y multiplied by 1/4, because this is the 4 that comes out of the derivative of the inside function, right? So this is it. Therefore, that's the answer, okay? Okay, guys, so now here it is. What to do if they ask you to figure out the derivative of an implicit function and when you see these products. All right, well, start by writing out the equation, right, that defines the implicit function y, right? And as usual, start by taking derivatives in both sides of the equation, right? Derivative with respect to x here, derivative with respect to x here. Next, follow your rules for derivatives, differentiation rules. Distribute your derivative over the sum or the difference, right? In this case, we have a difference, so we have to do this. Derivative of 3x times y with respect to x minus derivative with respect to x of y squared, right? Y squared. I'll put it within parentheses here. Okay, great. So this is what we have on the left side. On the right side, anyone could tell me what is this derivative? Derivative of the constant function 4 with respect to x?
0.
Excellent, guys, excellent. I'm glad that you are tuned 0, right? It's very common that in a lot of exercises related to implicit differentiation, this side is a constant. It's good, this will be, but not always, right? You saw it, right? Not always, but most of the time, this is derivative 0. All right, now it's time to take the derivative of 3x times y. Remember, guys, y should be thought as a function, right? As a function. So you should think of 3x as being a function f and y as being a function g. So you should think of using what we call our product rule, right? Product rule, f times g derivative equal to derivative of f times g plus derivative of g times f, or f times g prime is the same. All right, so let's do that carefully here, right? So I have to start by taking the derivative of this guy, right? Derivative of f, derivative of 3x. What is that? Well, derivative of 3x is just 3, right? It's the usual derivative 3. Now I gotta multiply that by the function g as it is. It's a y, so this times y, right? Plus. I'm taking this derivative, right? Now this derivative of y, this looks like the identity function, but in terms of y, that derivative should be 1, right? Should be 1. But since we are dealing with expression containing y, we have to attach dy dx, right? Dy dx, that's the derivative. But that has to be multiplied by f, the function f, which is just 3x, right? 3x. So believe it or not, guys, this is this. Minus derivative of this, y squared. Derivative of y squared is the derivative that comes to mind, 2y, right? 2y, but since we are dealing with expression in terms of y, remember, we have to attach the dy dx, right? It's like multiplying by the derivative of the inside function y. You got to think of y as a function, right? Yeah, great. Equal to 0, Now, what is left is just to isolate this guy, right? By combining like terms, factoring, but isolate this, get this by itself. Notice this one is just 3y. Let's simplify, right? 3y. This is just, let's rearrange nicely, right? 3x times dy dx, right? Minus 2y dy dx equals 0. I just rearrange it. One disappears as a multiplicator, right? As a factor. All right, now factor out this guy after moving this 3y over the other side. This you need to transpose it to the right side. To do that, subtract 3y in both sides. And you will get 3x dy dx minus 2y dy dx equal, this is 0 here, but 0 minus 3y here, right? Minus 3y here. Next step, factor out this common factor. Use this as a greatest common factor, factor this out. They are the same, right? I'm gonna put it up front here, dy dx up front. And what is inside once you take this out? You're removing this 3x inside, right? Or equivalent to dy dx into this expression. This cancels 3x there. Minus, minus. This guy into this expression, 2y times dy dx, this cancels, 2y here stays, right? Factor out dy dx. This is what we're doing here, right? Factor out dy dx. I just did that. Minus 3y here. Finally, in order to isolate this guy, I am going to divide both sides of this equation by precisely this guy, 3x minus 2y. Okay? 3x minus 2y. Dividing those two, this cancels, and I am left with dy dx equal to what? Equal minus 3y over 3x minus 2y, right? Allow me to keep the negative sign on the top because they're going to do something that is going to help you with the multiple choices. Now, this is my answer, right? This is my answer. But however, sometimes when you look at the multiple choices, your answer might not be there, right? So this is my answer, right? On the homework, it's not going to matter because no matter how you write your answer in the homework, it will take it, right? Computer will take it. But let's say in the multiple choice, you look for this and it's not there. Professor, this expression for my answer, I cannot find it on the multiple choices. Then equivalently, turns out there is another form for the answer. Multiplying both numerator and denominator, both numerator and denominator by -1, multiplying numerator and denominator by -1, then what do we get? Well, let's see. If I multiply this by -1, I will get, and let me rewrite it here because often this causes confusion, okay? Look, this was my first answer, right? And this answer is okay, but sometimes you don't find the form. So multiplying, as we said, right, by -1 the numerator and by -1 the denominator, then you will get a new form which is completely equivalent to the previous. This will be 3y positive now, right? And this one, look, this times this, -1 times -2y, 2y, -1 times 3x minus 3x, right? So believe it or not, guys, this answer, 3y over 2y minus 3x, and this other answer, they are equivalent. Right? They are equivalent. It's just that this one doesn't show the negative sign, which mathematicians like, right? So For multiple choices, try this. For homework, you can try this, so this doesn't matter. Okay, guys, so now using this technique, try to do something so we can move on. We're gonna move on. I'm gonna give you something that is not that difficult. This one, for example. What about this? Yeah, there are questions there. Maybe this one. Number 2. Question here. Would it ever be like that on the test? Yeah, I said, right, for that test, try to base your studies on the worksheet. Now in this question you will see, but we're going to use that trick. So questions for the worksheets, yes, they could be on the test, right? But again, for the homeworks, I'm saying, right, if it's too difficult, that's a homework question, but let's pay attention to the worksheet questions, right? Yeah. All right, let's try to do number 2. Can you try to do number 2? I'm going to give you the hint and then I will let you work, okay? This is the equation that defines the implicit function y. First step, you have to take the derivatives on the left side, on the right side, right? And for that, distribute and then use the product rule for this, right? For the product rule, this will be your f, this will be your g, right? Product rule. F times g, derivative is f prime g plus g prime f, right? Use that for this part when you distribute, right? Yeah. This will be a good way to explain the question that was posed before. Yeah, let's do it together probably. And if you figure this out in the meantime, just let us know. Okay, so taking the derivative on both sides will lead to the following, right? Derivative with respect to x of 2xy minus derivative with respect to x of y squared, right? That's what I got on the left. On the right, I'm taking the derivative of the constant function 1. This is just 0, right? 0. Good news there. Great. Now, I gotta be careful here. Is a multiplication of two functions. Multiplication of two functions, Professor. Well, this is the function f twice x, and this is the function g, y, right? Yeah. So follow this multi-product rule. Product rule says first take the derivative of the first factor 2x. That's 2, right? That's 2. I see students figure this out. That's 2. And Adriana, yeah, you got it, Adriana. Very good, excellent. Yeah, okay, so let's go there. So derivative of 2x2 multiplied by g, which is y, right? Plus derivative of y. Derivative of y is 1, right? 1. But since we are dealing with an expression containing y, we have to attach the dy dx, right? We explained this, right? It comes from the chain rule. Yeah, that's that. But then we have to multiply this by the other function f, which is twice x. Twice x. Minus derivative here of y squared. More students are posting answer. Grace, very good. Adriana, Sarah, yeah, you guys figure it out. Very good, guys. Yeah, so minus derivative y squared. The derivative that comes to mind when you take derivative y squared is 2y, right? But since we are dealing with an expression containing y, remember you have to attach dy dx. And that all equal to 0. Now, this is twice y, right? Twice y. And this other guy is 1 times 1 disappears as a factor, right? So this will be 2x. Allow me to write it here, dy dx. I'm just organizing myself. You know, this is this, right? Minus 2y dy dx equals 0. Now remember, we have to move, we have to transpose this to the right side. For that, we subtract 2y in both sides, right? The 0, this is going to be the following: 2x dy dx minus 2y dy dx equal minus 2y, right? Minus 2y. Very good. Yeah, we will continue here. Factoring out this guy, the dy dx, right? Which is the same here, factoring it out. I hope you will be okay with this. Dy dx will be equal to dy dx outside, sorry, inside 2x minus 2y, right? Factoring it out. Equal what? Negative 2y. And look at this, guys. Once you divide both sides by this, 2x minus 2y, to isolate your dy dx, right? Look what's going to happen. Dy dx is equal to what? Minus twice y over 2x minus 2y, right? Now, there's a number 2 that I can factor out and simplify, right? But even if I do that, notice that this answer does not appear clearly on the choices, right? Look, if you look for this answer on your multiple choices, minus y over x minus y, does it appear there? Look, it's nowhere to be found here, right? But do not panic, guys. On those cases, when you don't see your answer, this in a homework problem, you post this, it will work. But on, let's say on the exam, you look at this, right? Professor, my answer is not there. But don't panic, just follow the trick that I gave you, right? Multiply numerator and denominator by minus 1, right? This is not going to change the value of the fraction, but it will give us a new version, an equivalent version of the fractional expression here, y minus or minus plus, right? And here, look, minus 1 times minus y minus 1 times x minus x. But this is the same as this, right? I want you to follow this, guys. This expression algebraically is the same as this mathematically, right? They are both the same, different forms of the same thing, right? So, but the advantage of this form is that this appears here, right? Is this. You follow it? Yeah. All right? Yeah. And so it's a very common trick, right? A common trick to be able to identify your answer, right? Follow that. Yeah, this is similar, guys. I hope you can do it at home. Let's move on to the other particular cases. We did this algebraically, completely. Dy dx was found as a formula in terms of y and x very often, right? Good. But what if they ask you to do this in particular for a particular value of x or for a particular value of y? Well, let's explain that nicely, okay? Yeah, and if needed, we will go back to more examples there. So, what are you talking about, Professor? Well, I'm talking about something like this. I will show you. It's example 4. Suppose they say, find the slope of the line tangent to the hyperbola x squared minus y squared equals 16 at the point 5, 3. Okay, guys, before I go over this, I want you to understand what's going on here, okay? Hyperbola, Professor, what is a hyperbola? Well, if you pull out your Desmos scientific calculator, the graphing calculator here, turns out this scientific calculator, graphing scientific calculator, it also graphs this type of equations. So let's graph it, okay? So x squared minus y squared equal 16. That's the graph of this equation, right? It's not a function, right? It doesn't pass the vertical line, but it's the graph of this equation. So what they're trying to ask you here, what they're asking you here, is to figure out the equation of the tangent line at this point, 5,3. 5 is here on the right, 3 is here up, right? So you can draw a tangent line here, right? And what they are asking you is the slope of that tangent line. You follow, guys? A slope of that tangent line, okay? All I know in advance by looking at this graph is that the slope should be positive, right? Because it's an increasing line if you walk along the line from left to right, but I don't know numerically how much it's gonna be, right? So we will find out, right? But that's what they are asking you to do here, right? The equation of this tangent line at 5,3 at this point, right? This figure is called a hyperbola, okay? Okay, it looks like the disjoint union of two sideways parabolas, right? Yeah, it's called hyperbola. It's an important figure, I think, in mathematics and physics, right? All right, so let's do that, right? Let's figure out the slope of the tangent line there. So first, I'm gonna follow just the traditional method, okay? And then I will give you a shortcut, a very important shortcut. First, if I follow my traditional method, okay, Professor Retamon said that whenever you deal with an implicit function, you should take derivatives in both sides, right? So we're gonna do that. Derivative here with respect to x, derivative here with respect to x, right? And then, okay, if I take the derivative of this guy, that would be the derivative of x squared with respect to x. Let's write it out first. Minus derivative of this component, derivative of y squared with respect to x, equal derivative of this constant function. We all know at this point, right? It's just 0, right? 0 is a very common form. Okay, but now derivative of x squared, what would be that? Well, that would be 2 coming down, multiplying x, right? Raised to 1 less 1. Minus. Here, the derivative of this guy, what is it? Well, the derivative that comes to mind is 2y, right? 2y. But since this expression is in terms of y, not in terms of x like before, right? We have to attach this dy dx, right? This dy dx. That equals 0. Now, guys, I have to isolate this guy, right? Because this derivative, remember, will give me the slope of the tangent line, which is what they're asking me to find, right? Find the slope tangent line. That's the derivative at this point. All right, great. So now, in order to isolate this guy, what I'm going to do is I'm going to subtract twice x in both sides, okay? Twice x in both sides. To eliminate this guy, I will be left with minus twice y dy dx equal minus twice x, okay? And dividing both sides of this equation by whatever I have here in front of dy dx, in this case is minus 2y, right? Dividing by minus 2y both sides of the equation, I get to isolate my dy dx. Turns out it's just x over y. Negative and negative positive, 2 divided by 2, 1. This is it, right? Okay, now they want this derivative, the slope of this, the tangent line at this point, 5,3, right? At 5,3. So then at x equal 5 and y equal 3, the slope of the tangent line should be equal to what? I use the formula I just got there, right? Which is this, right? X over y. And I substitute x is 5, y is 3, right? Y is 3. So this is it. I am done. This is the answer to my problem, right? Now, guys, this was the straightforward method, the one that requires computing this first symbolically, like you can see, right, as a formula, and then substituting the values, right? But now, turns out this process may be tedious, especially if this equation is complicated. You saw the exercises before, right? Some of them are not so easy to compute, right? These formulas. So because of that, whenever you are asked to compute the slope of a tangent line at a given point, right? Whenever they give you a specific coordinates for you to do that computation, you may follow this other method. I'm going to write it here next to this as an alternative, okay? Alternative here. So let's write it in my alternative. Alternative. It's going to be like a shortcut. Here, you start taking the derivative in both sides. But when you are here, right? Maybe we should write this still so nobody gets confused. You still take derivatives in both sides. Okay, this is okay. Derivatives in both sides. Here, you're going to get twice x. Here, twice y, dy dx, right? And here, c. Till here is the same. But here, instead of isolating dy dx, like you did here, you do the substitution of x and y directly here. I want the slope of the tangent line at x equal 3, right? Or x equal 5, I believe so. Sorry. Let's check well. I want this at x equal 5 and y equal 3, right? So directly you substitute here your x equal 5 and here your y equal 3, okay? And your slope dy dx, you call it m, okay? And then you just solve for m. Now, solve for m. So you forget about the general equation and you solve this for m. And if you do that, you will see that we're gonna get the same answer. This is 10. And turns out this is gonna be a nice shortcut that's gonna help you in your homework. And in a lot of exercises, 2 times 3, 6, m equals 0, right? And here, all you gotta do is to solve this for m. So minus 6m equal minus 10. After you cancel these two, right? And dividing both sides by -6, there you will get your final answer. After canceling this, m equal negative and divided by negative positive, dividing by 2, dividing this by 2, you get 5/3, right? Same, right? As you can see, I'm going to point that out by saying same. But this method does not require this formula, right? This is the goodness of this alternative, okay? So directly substitute the values of x and y on the equation that you get after taking derivatives and then solve for m. That will give you the slope, okay? Okay, guys, let's see how this shortcut works. Let me go to the worksheets. And let's show something there. For example, I'm going to give you this as an example, right? And then I will ask you to do something else, perhaps this one. Right? Okay, let me show you how the shortcut works very nicely here. For example, here they are giving you this equation, y raised to the 4th power plus x raised to the 3rd power equal y squared plus 10x. And they are asking you to compute the slope at this value, 0,1, right? Not just in general, but at this particular point, right? So let's do that following the shortcut. Because if you follow the traditional method, it's going to be very long. So if you follow the alternative, the shortcut I just gave you, you start by taking the derivatives here with respect to x. And here, derivative with respect to x as well, right? Derivative of y raised to the 4th power is just equal to 4y raised to the 3rd power, since we're dealing with expression containing y dy dx, right? Dy dx plus the derivative of x cubed, the derivative of x cubed is equal to 3x squared, right? Derivative of y squared, again, an expression containing y, derivative that comes to mind is 2y, but since the expression is in terms of y, I have to attach dy dx, right? Dy dx plus derivative of 10x is just 10, okay? Now, normally I will have to isolate this guy, but this takes a long time. Instead, since you want this derivative, this slope of the tangent line at 0,1, directly substitute 0 for x and y with 1, right? Y is 1. I want the slope here. Dy dx is going to be the slope of the tangent line. I will represent it with m plus 3x. What is x? 0. 0 squared. Right? Directly, I'm replacing the value of x and the value of y. 2 times y. Y is 1. A slope, I represent it with m. Okay? This m and plus 10. And then I just solve for m. Now solve for m. That's all you gotta do, guys. Look, 1 cube, 1 times 1 times 1 is 1 times 4, 4m there. 0 squared is 0, kills this term. 0 times 3, 0. Here, twice m, right? Plus 10. Subtracting 2m in both sides, I get 2m equal 10. Dividing by 2 both sides of this equation, I get that m is equal to 5, right? The slope of the tangent line at 0,1 of this curve is equal to 5. You follow, guys? It's a good shortcut because imagine computing or isolating dy dx, right? And then replacing it would take too long, right? Follow this shortcut is a good one, right? That was for question 6. Let me see if I can give you something for you to work on. Yeah, I think yeah, this was finding the slope. Let's see if I can give you something similar. Yeah, let's try this. Can you try this on your own? Either with a shortcut or with the traditional method that we follow, right? And then we will find equations of a line. Yeah, this is the equation x to the 4, y to the 4 equals 16. And they want you to find the slope. Find a slope at this point, 2, 1, the slope of the tangent line, right? And remember, this is x, this is y, after you take derivative in both sides, right? So follow that shortcut and figure this out, guys. So take derivative here with respect to x. Don't forget to use product rule there, right? And derivative with respect to x here, which is going to be 0, right? 0. Yeah, as a hint, I'm going to give you here that you have to use product rule here. Product rule with this guy F and this guy G. Recall derivative of F times G, F prime G plus G prime F. Okay. For the side here, the derivative is 0. And then follow the shortcut, right? Once you take the derivative, replace x with 2 and y with 1. Okay, let's try to do it together. Okay, if you get the answer, just let us know. This is going to help a lot on your homework, guys. Okay, so if I take derivative on the left, I have to start with the derivative of x to the 4. That is just 4x cubed, right? 4x cubed. Then I multiply this derivative by g. The function g is y to the 4 power, right? That. Plus derivative of g, derivative of y to the 4 power is 4y to the 3rd power. That's the derivative that comes to mind. But since I am dealing with expression in terms of y, I have to attach dy dx, right? Dy dx. That's just the derivative. But then I have to multiply that by f. F is x to the 4. This is what I get on the left side. On the right side, derivative of constant functions, 16 is just 0. Good. Now, I want to find the slope of the tangent line, not just in general, right? Not in general, but at this particular point, right? Let's take advantage of that, right? If you want, Oscar. Very good, Oscar. Yeah, very good, very good. Very good, Oscar. You may be there. Grace also, very good. Yeah, very good, guys. So, since I know what is x, what is y, x is 2, y is 1, let's just replace the values of x and y here, right? Here, let's take advantage of that. Yeah, so I replace the values there. So then I will get 4 times x cubed, but the x is 2 cubed, y to the 4 power, y is 1 to the 4 power, plus 4 times y is 1, raised to the 3rd power, derivative, the slope of the tangent line, and we'll replace this by m, times x to the 4 power, but x is 2 to the 4 power equals 0. I gotta do this in a calculator. This is 8 times 4, 32. This is just 1, right? So this is 32. 1 cube is 1, 4m times 2 to the 4 power is 16. 16 times 4, 64 m, right? And this computation, guys, if it's difficult for you to get it on your mind, use the calculator, right? But now subtract 32 in both sides. 64m equal minus 32, right? And then dividing by 64 both sides. Yeah, Adriana, also very good, very good. Yeah, you got it. Yeah, very good, very good. Dividing by 64 both sides of this equation, I get that m is equal to m equal minus 32 over 64. But simplifying, right? Simplifying, this is just minus 1/2. Right? Excellent, guys. Excellent. This very good. Right? You see the shortcut is good because otherwise you have to isolate this, might not be so easy, right? Yeah, so follow the shortcut is a good one. Now, sometimes they are going to ask you to do this, but they will ask you to go one step forward. They will not ask you only for the slope of the tangent line, but they will ask you for the equation of the tangent line, right? But that shouldn't be a problem. Let me show you this number 9, and then I will ask you to do some other question, okay? This number 9, let me show it to you. Suppose they say, okay, this is an equation that has some graph, right? You can even find it if you use your grapher, right? If you wanna know how it looks like. But what is interesting here is that they want the equation of the tangent line, not just everywhere, not as a general formula, but at this particular point, right? So quickly, we just keep in mind that we have the values of x and y, right? X is 0, y is 1. All right, so let's follow the first step for implicit differentiation, which says take derivatives in both sides of your equation with respect to x, right? Derivative of y raised to the 5th power with respect to x is the derivative that comes to mind, 5y to the 4th power, dy dx, right? You may say, Professor, why you are attaching this? Because I'm dealing with the expression in terms of y, right? When I take the derivative here, I don't have to do that, right? So here, 3x squared is the derivative. Derivative here 2y dy dx, right? Plus derivative here, just 9, right? Just 9. At this point, I can substitute x with 0, y with 1, right? So let's do that. 5 times y raised to 4 power, but y is 1. 1 raised to 4 power. dy dx, I will substitute it. I will call it m, right? Slope that I'm looking for. 3 times x is 0. 0 is squared. 2 times y is 1. Multiply by dy dx, the derivative is the slope of the tangent line. Let's call it m, plus 9. 1 to the 4 power raised to 4 power, better said, is just 1 times 5, 5. 5 times m plus 0 squared is 0 times 3, 0, right? The whole thing 0. This is equal to 2 times m plus 9. Subtracting 2m in both sides of this equation, I get that 3m is equal to 9, and therefore m should be equal to 3, right? M is equal to 3, divide both sides by 3. I found the slope, but doesn't end there, right? Slope is 3 of the tangent line. But now they want the equation of the tangent line. Find the equation, they say here, right? Equation. So I have to go one step farther, but this shouldn't be a problem because we have a way to figure out the equation of a line when we have the slope of the line and a point, the coordinates of one point of the line, right? This is this. It's called point slope form. Y minus 1 equal slope 3 times x minus x1 is 0. This 0 disappears. Y minus 1 equal 3x. Adding 1 to both sides of this equation, we get that y is equal to 3x plus 1, right? This is the equation of the tangent line, right? To the graph of this curve, the one represented by this equation, right? All right, so then look through is here, right? Very good. Yeah, so the shortcut helps. Let's take a look at this now. Let's see if we can do this one. Can you try this one? Let me see which one is better. Yeah, this one probably is good for you. Try this. Can you try this? I'm gonna write it out. They want you to y minus pi cosine of y equal 7 pi. So find the equation of the tangent line. Find the equation of the tangent line, right? At point 1 comma pi, right? It's not that they want the slope of the tangent line everywhere, right? They just want that slope here, and further they want the equation of the tangent line, right? So you can count on x being 1 and y being pi after you take the derivative, right? So try to do this, guys. Go ahead. The hint is start by taking the derivative with respect to x on both sides, right? And then you have to use product rule there, right? So, yeah, it's a bit tricky. Try to keep pi as pi symbolically kind of, right? So do not replace it by 3.14. As you can see, the answers, they all contain pi's, right? So keep it as pi. The hint here for this part should be, in order to use the product rule, you have to call this F, right? Represent that with F and represent this with G. I probably have right recall. derivative of f times g equal derivative of f times g plus derivative of g times f, right? Yeah, use that. All right, let's try to do this together, okay? So if you eventually find the answer, let us know. Okay, so if we distribute our derivatives here, we have to take the derivative of 6x squared times y with respect to x minus, allow me to pull out the constant pi and focus completely in the derivative of cosine of y with respect to x. Okay, this is what we're gonna do, right? And this derivative, the derivative of the constant function 7 pi is just 0. Very good. Now, for this part, we said we're going to call or represent this 6x squared by f, this by g, and we're gonna use our product rule, right? Product rule. Product rule says start with the derivative of the first factor, which is 6x squared. That derivative is gonna be 2 coming down multiplying 6, 12x, one less exponent, remember? Right? Times the other function g as it is, y, plus derivative of g now, derivative of this guy, derivative of y is 1. But since I am dealing with an expression in terms of y, I have to attach this dy dx, right? Dy dx. That is the derivative of this g function. But then you're gonna multiply that by the f function 6x squared, right? 6x squared. This is this. Now, what is this? Well, this is minus pi derivative of cosine of y. Derivative of cosine is sine, but negative, right? Negative sine. So let's write it this way, negative sine of y. But since I'm dealing with an expression in terms of y, I have to attach that dy dx. And this is just 0. This is 0. So notice minus and minus plus, right? Plus. So let's rewrite this whole thing nicely clear. Xy plus dy dx, and here is 6x squared, minus and minus plus, right? Plus pi sine of y dy dx. Now, the good thing here is that they want the equation of the tangent line at this given point, right? At this given point. So I have here the right to call my x just 1 and my y, that should be just pi, right? I can replace or substitute these values directly here, right? I don't have to isolate dy dx, right? So 12 times x, which is 1, multiplied by y, which is pi, plus dy dx is going to be the slope of the tangent line. I will call it just m. 6x, but x is 1, is squared, plus pi sine of y, but y is pi. Dy dx, I can write it as m, right? M here equals 0. Now, this is 12 pi, right? 12 pi. Let's keep pi, right? As it is. This is 1 squared 1 times 6m here. Plus, notice sine of pi is 0, right? From the unit circle, 0. So this whole thing is 0. So this disappears. This is equal to 0. Now, sine of pi is 0, Professor. If you don't remember, guys, you can get it in your calculator. Sine of pi in radians, 0, right? In radians always 0. All right, great. So we have this. Now we can subtract 12 pi in both sides. We get 6m equal minus 12 pi divided by 6 both sides. The slope, believe it or not, guys, is just negative 2 pi, right? That's the slope. Good. Now, but it doesn't end there because they want you to compute with this slope, negative 2 pi, and the point is here, 1 comma pi, the equation of the tangent line, right? But it shouldn't be difficult because we have this form, it's called point slope form, which allows us to compute the equation of a line when we have the slope and the coordinates of one point of the line, right? This is my x1, this is my y1, this substitute in here, y minus y1, which is pi, equal a slope negative 2 pi times x minus x1, 1. Let's work it out. Y minus pi equal minus 2 pi times x. Minus 2 pi times minus 1 is plus 2 pi, right? Minus 1 is plus. And finally, guys, adding pi to both sides of this equation leads to 0, y equal minus 2 pi x, 2 pi plus 1 pi, there's an invisible one there, 3 pi, right? 3 pi. And this should be it. This should be it. And this is minus 2 pi x plus 3 pi. I think that's number 10. Yeah, very good, very good. Excellent, excellent, guys. Very good. Okay, now probably to finish, we should look at this quickly. Yeah, I'm gonna just do it for you to help you out with your homework problems. 4x squared y minus pi cosine of y equal 5 pi. They want you to figure out just the slope, not the equation of the line, just the slope, right? At what point? At this point, 1 comma pi, right? So quickly, you take derivatives, right? Both sides. Derivative of this part is going to be, if you let this be f and you let this g using the product rule, will be the derivative of this guy is 8x times the other function y plus derivative of this guy 1 dy dx times this as it is 4x squared minus notice this one pi derivative of cosine minus sine of y, right? And you have to attach dy dx, right? This equal derivative of 5 pi 0. But now the good news is that we have the value of x is 1, the value of y is pi. So put them in. So x times x, which is 1, y pi, plus 1 times derivative, I call it m, 4, 1 squared, minus pi, minus sine of pi, dy dx, equals 0, right? But now sine of pi, remember, is 0, so kills all this part. And dy dx, we said we should write it as an m, right? So don't worry about this part. This, we call it m. So anyway, this is going to disappear because this is just 0. All right, so now we have here pi plus, this is 1, 4m equals 0. Okay, so don't forget the 8 here. Now minus 8 pi here, minus 8 pi here. 4m equal minus 8 pi. Dividing both sides by 4. There you have your answer. M equal minus 2 pi. M equal minus 2 pi is here, right? So for number 7, very good. Yeah, just for you to see, guys, that this shortcut of replacing the values, right, of, in this case, x and y for what they give you there, right here, pays off, because look, you get to eliminate all this part and quickly you get your result, right? All right.